Welcome to Module 7, Fans, Duct Systems, and Variable Air Volume. In this module, we connect what the VAV displays on the screen to what is really happening in the air system. A fan speed command is not the same as airflow. A damper position is not the same as ventilation. And a duct static pressure value is only useful when we know exactly where the sensor is installed and what pressure reference it is using. As we move through the module, keep asking one question. Does the data describe the physical system, or is it only describing a control point? By the end, you should be able to review fan speed, VFD status, duct pressure, VAV demand, airflow trends, and comfort conditions as one connected system. This module has 6 practical objectives. First, you will learn how the fan operating point is created by the intersection of the fan curve and the duct system curve. Second, you will use the affinity laws as useful estimates for speed, pressure, and power, without treating them as guarantees. Third, you will learn how to read VFD command, feedback, limits, faults, and bypass status. Fourth, you will evaluate static pressure reset logic using verified demand. Fifth, you will connect VAV airflow, damper position, zone demand, minimum airflow, and ventilation. Finally, you will apply these ideas to field troubleshooting, where the best answer is often not to raise the pressure, but to verify the evidence first. Start with the whole system. The fan creates a pressure difference. The ductwork, coils, filters, dampers, fittings, and terminal units consume that pressure. The VFD changes fan speed, but the duct system determines what airflow results from that speed. The static pressure sensor reports one location, not the entire duct system. VAV boxes react to zone demand, minimum airflow, available inlet pressure, and their own measurement accuracy. Return air, relief air, exhaust, and outdoor air also affect building pressure. A professional does not diagnose the system from one point alone. We look for relationships: speed to pressure, pressure to airflow, damper position to demand, and airflow to comfort, ventilation, and energy. The fan operating point is one of the most important concepts in air system troubleshooting. A fan has a performance curve. The duct system has a resistance curve. The actual airflow happens where those two curves intersect. That means a 60% fan speed command does not guarantee 60% airflow. If VAV dampers close, filters load, coils foul, a fire damper restricts the duct, or outdoor air paths change, the system curve changes. The fan may be doing exactly what it is commanded to do, while the building still receives the wrong airflow. When diagnosing, compare command, feedback, duct pressure, airflow, damper positions, and actual field conditions before changing the set point. The fan affinity laws are powerful, but they must be used with judgment. For the same fan under similar conditions, airflow changes roughly in proportion to speed, pressure changes roughly with the square of speed, and power changes roughly with the cube of speed. This is why reducing speed can create major energy savings. For example, reducing speed from full speed to 80% can reduce theoretical fan power to about 51%. But that is an estimate, not a guarantee. Real systems include changing fan efficiency, air density, damper position, filter loading, and system resistance. Use the affinity laws to guide your thinking, then verify the result with trends and measurements. VFD is an enabling technology. It gives the BAS a way to change fan speed, but it is not the complete strategy. When you review a VFD, follow the complete chain: BAS command, command source, handoff auto status, minimum and maximum frequency, acceleration time, actual speed feedback, current power, fault status, and bypass status. BAS may show a valid command while the drive is in hand mode. A drive may be at 60 Hz while airflow is still low because the duct system is restricted. A drive may be at low speed, but that does not prove cube law savings. Always confirm what is commanded, what the drive is actually doing, and what the air system is delivering. Supply fan control often depends on a duct static pressure sensor, so sensor location is critical. If the sensor is too close to the fan discharge, turbulence and local pressure effects may not represent the distribution system. If the sensor is placed in a poor branch, it may miss critical zones. A fixed pressure set point is simple, but it can waste energy when most VAV dampers are nearly closed. A reset strategy can reduce pressure during light load, but only if it protects ventilation, comfort, noise, and critical zone performance. The BAS can only control from the information the sensor provides, so location and reference must be correct before the logic can be trusted. A robust static pressure reset does not follow one unqualified signal. It starts with a selected group of representative terminals. It rejects failed, overridden, or unreliable boxes. It uses minimum and maximum pressure limits, slow reset rates, and persistence so the fan does not chase short-term noise. The sequence should also include fallback behavior. If the demand data becomes unreliable, the system should return to a safe default and generate an alarm. The purpose of reset is not simply to lower pressure. The purpose is to supply enough pressure for verified demand while reducing fan energy and avoiding unnecessary reheat, comfort complaints, noise, and unstable operation. A pressure-independent VAV terminal can maintain airflow only within a useful operating range. The controller compares airflow set point to measured airflow and modulates the damper, but the measurement depends on pickup tubing, the correct K-factor, adequate inlet pressure, and reliable velocity. If a box is calling for 1000 CFM and reports 650 CFM with the damper fully open, do not immediately raise the system pressure. Check inlet pressure, tubing, pickup condition, flow coefficient, damper linkage, upstream restrictions, and whether the airflow is below the reliable sensor range. The VAV box is part of a system, not an isolated device. AI avatar narration script. Minimum airflow is a professional decision, not only an energy-saving setting. Minimums may be required for ventilation, pressurization, heating performance, air distribution, process requirements, or the reliable measurement range of the terminal unit. Reducing VAV minimums can reduce fan energy and reheat, but it can also create underventilation, unstable airflow readings, poor mixing, cold drafts, pressure problems, or heating complaints. Before changing minimum airflow, verify space use, occupancy assumptions, ventilation requirements, terminal capability, reheat strategy, and any special pressure or process need. The lowest airflow value is not automatically the correct value. AI avatar, narration script, economizer operation must be coordinated with return and relief. When outdoor air dampers open, the building receives additional air. That air must leave through a return fan, relief damper, exhaust system, or a leakage path. If the relief path is not coordinated, the building can become overpressurized, doors can become difficult to open, and uncontrolled exfiltration can occur. If exhaust or relief is excessive, the building may become negative. Do not treat outdoor air damper position as an isolated sequence. Review the full path: outdoor air, mixed air, supply airflow, return airflow, relief airflow, exhaust, and the building envelope. AI avatar narration script. This case study shows why reset logic must protect itself from bad data. A campus resets supply static pressure using the maximum damper position across all VAV boxes. One box fails and remains at 100% damper command. The BAS interprets that as continuous high demand and drives the fan toward maximum pressure all day. Energy rises, noise may increase, and the real problem remains hidden. The correction is not simply to lower the pressure set point. The correction is to reject failed and overridden boxes, use a selected terminal population or robust statistic, alarm persistent outliers, and repair the bad terminal evidence. AI avatar narration script. Most fan system mistakes come from treating one point as the whole system. Command percentage is not airflow. Affinity laws are estimates, not exact measurements. A static pressure sensor at the wrong location can mislead the entire control strategy. One failed VAV box should not control the fan. Minimum airflow should not be pushed below the terminal's reliable range. Outdoor air should not be changed without checking return and relief. And low airflow should not automatically mean raise the fan pressure. Good practice is to verify the chain: command, feedback, measurement, physical movement, airflow, space result, and energy impact. AI avatar narration script. Use this checklist before making fan or VAV sequence changes. Confirm the fan curve and design point. Verify the VFD command source, limits, handoff auto status, feedback, fault status, and bypass condition. Trend speed, current power, static pressure, and terminal demand. Confirm that the static pressure sensor location is appropriate. Review reset logic for bounds, persistence, and bad data rejection. Verify VAV pickup tubing, calibration factors, minimum airflow values, and terminal reliability. Confirm return, relief, and exhaust coordination. Finally, evaluate fan energy and reheat together, because reducing fan power while increasing reheat is not a complete optimization. AI avatar narration script let us apply the reasoning. A VAV box reports 650 CFM when the set point is 1000 CFM and the damper command is 100%. The quick reaction is to increase the fan static pressure set point. But before doing that, verify the physical and measurement chain. Is inlet pressure actually low? Is pickup tubing connected and clean? Is the K factor correct? Is the damper moving? Is there an upstream restriction? Is the terminal below its reliable sensing range? The best answer is B. Evidence comes before pressure changes because unnecessary pressure increases waste energy and can hide the real fault. AI avatar narration script. For the practical assignment, design a static pressure reset review. Choose a representative group of VAV boxes. Define how the sequence will reject failed boxes, overridden boxes, bad airflow values, and short-term noise. Establish minimum and maximum pressure limits. Select a slow reset rate and a persistence rule. Define fallback behavior and operator alarms if demand data becomes unreliable. Then explain how you will verify ventilation, comfort, fan energy, reheat impact, noise, and stability. The core lesson is this: fan systems should be controlled from verified relationships, not isolated points. In the next module, we move from air systems to hydronic fundamentals.